So now we're getting to a new chapter and the last chapter to cover this class of broad topics regarding security, and that is operating system security, which is chapter 5 in your textbook. Review some very interesting topics. First, we're going to talk about operating systems in general, how they work, what are their main ingredients, and then a little bit about their history, and then we're going to discuss about security in operating systems, which is integrated to them. We will discuss a very important concept in security, the concept secure by design, and finally, one of the most grave vulnerabilities of operating systems, rootkits. We begin with the question of what is an operating system, and some of you may be already taking the operating systems course or have already taken it. So I'll give you some definitions and some basics. Of course, I don't assume that you have taken this class. So the fundamental controller of all system resources is the operating system. And because it is the fundamental controller of all the system resources, it is the prime target of adversaries. An operating system at boot time initiates all the primitive functions that are needed for a system to operate, such as inter-process communication, basic input-output, and then as it loads more complex functions, such as files, directories, and memory segments. And then even later, it may load antivirus systems, and that later means that it might be too late to defend the fundamental operating system operations. So that is why an operating system has to have its own security mechanisms and not rely on additional software. We also need to bear in mind that it's not only our personal computers that have operating systems. Nowadays, of course, our phones have operating systems. The Android phone has the Android operating system, and the iPhone has the iOS. And of course, the Internet of Things devices have operating systems of their own. Some of them more minimal, like Linux, minimal versions, light versions. Most of these are variations of the Linux operating system BusyBox. And some of them are more complex, and some just have firmware like a digital assistant. So do not consider that every single IoT has an operating system, even a smart light, for example. These don't have operating systems. But lots of Internet of Things devices have sufficient operating systems. Operating systems are a primary target to adversaries, and that is why they have security features embedded into them. So there's a list over here and kind of giving the big picture, and we're going to get into more details. So one security feature is enforced sharing, which is making resources to users available as they are appropriate and not, making everything available to everyone. Inter-process communication. So in the process of communication, it's about synchronizing resource access and mediating access based on access control tables. So the control tables are prevalent in terms of security features for an operating system. Protection of critical operating system data can be done with protection from unauthorized access, the read-write permissions that we have already discussed when we were talking about access controls, read-write execute, actually. And then it can be guaranteed, this protection, by using encryption, hardware control, and of course, isolation of parts. Guaranteed and fair service, another security feature of an operating system, that is about not depriving any users from resources and being fair and scheduling resources fairly. Interface hardware, again, in this case, it's about fairly accessing not just resources like software resources, but also hardware resources. And this is achieved by using hardware clocks and of course, again, control tables. User authentication is another security feature of the operating system, and it has to do with making sure that the user that says they are the legitimate user of the system are who they claim they are, and this is usually achieved by passwords, but nowadays also we see more and more biometrics for this type of user authentication. Memory protection is very important since the operating system has complete access to the memory of your system. There's lots of fun stories to think about that and attacks. Buffer overflow, great example. So memory protection can protect from unauthorized access. And it's a defense for buffer overflow by restricting parts, like restricting the kernel, which is a very important part of the operating system, is a security feature, a very important security feature. Now, device access control, input-output device access control, and file access control. Again, we have discussed this also when we were discussing about access controls early in the semester. And this one has to do with protecting user and system files from unauthorized users. And we've discussed even in the beginning of the semester how this is implemented in the two major operating systems, Linux and Windows. Last feature of security for operating systems are location and access control for general objects. These are constructs, abstractions that permit concurrency and synchronization, and through table lookup, we achieve protection of these protection and access control. Learning about the history of operating systems briefly will help us understand how they were developed and how their security mechanisms were also integrated. So operating systems started as single user. That was a time that there was not much hardware to be controlled, like keyboard and mouses. It was a time of punch cards where users had to load even their compilers and whatever tools they were using, and load the program that they had to use, and then use the system, and then clean up everything for the next user to come over and use this same system. Now, as computers kept progressing, we had multi-programmed multi-programming, and that was a change from single user to multiple users, and then that was the beginning of operating systems that at the time were not called operating systems, they were called monitors, and they would arbitrate the resources that they would give to users when they considered that that the request was for the general good of the system, which means, again, in terms of fairness and fair allocation of resources. The controlled sharing implied security, and that security was lost when the personal computer became dominant. When the personal computer became dominant, we did not anymore have these multi-programming, multi-user systems, the time-shared systems. We now have the multitasking systems. So there are some definitions over here to explain multitasking. First, a process is when a user runs a program, it consists of a process. Now, the resources that the process uses are called a domain. And then a thread is executing, is a stream of execution, and it executes in the same domain as all other threads for a process. And as you know, your programs are multi-threaded, your software is running in multiple threads, but all in the same domain for the specific program with the specific resources. So finally, a thread may spawn one or more tasks, and that's where the multitasking is coming from. And tasks can be interrupted depending on what they're doing, voluntarily or from the operating system to arbitrate and ensure fairness. So that's how multitasking came in, and that, because of these shared resources, started causing some security issues that had to be taken care of with embedding security into the personal computer operating systems. Finally, the protected objects in operating systems that are discussed later on when we have PCs and all that. The protected objects in the later operating systems are memory, shareable input-output devices, so definitely no input-output devices in the very old systems, the punch card systems, shareable programs and procedures, and all of these needed to be protected, and they were in this category. Now here we see a view of the modern operating system that is layered and with functions arranged from the most critical one to the least critical. And when we say critical, we mean security critical. So the most critical, of course, is hardware, and then we go to security functions and so on and so forth. And the least critical could be an interface or an add-on or something along those lines. And this is a different view of layers, not in this vertical view, but in a cyclical view. And it shows again really well that the outer circles are the least trusted code, such as, for example, the text box that you put your password for to authenticate in your operating system. That's the least trusted code, and it can be on the outer ring of the circle. And then the most trusted is changing the password or authenticating, verifying the password and all that. Shows the operating system modules. And as you can see, again, these are layered, and these are modules that can be found in most modern operating systems. There is a lot of complexity to handle devices, for example, hardware devices that come from different manufacturers, and therefore the software that controls them, the device drivers, come from third parties. So, for example, your Windows operating system uses a device driver for the Dell keyboard, and maybe another device driver for your HP monitor, and so on and so forth. So different manufacturers, different device drivers, and all of these need to be put together from the operating system. On top of that, there's programs like the antivirus that hooks and is incorporated to the operating system and has enhanced privileges. And you can imagine that it's very difficult to make everything work and make sure that the software that comes from several third parties, also the drivers, are not malicious. It's also very complex to change things in an operating system. Like, for example, sometimes you see the interface changing in your operating system, new themes and all that, and you think that this is probably simple, but replacing a file system or a user interface requires integration with several of these levels that you can see in this picture. So it's complex, it has a difficult job to do, the operating system, and at the same time, it must protect itself to protect its users. I'm going to review in this specific video is how the operating system is loading. And as you can see in this picture, it is loading in multiple stages. It's not a monolith because of its complexity and its importance. It loads in parts. So first is the BIOS, which is input-output support for access to the boot device, hardware abstraction, firmware, and things that are hard-coded in hardware. Then the bootstrap loader is loaded, which is like pulling the operating system by its bootstraps, fetches the next parts of the operating system. Then the primitive kernel is loaded, which, as I've mentioned before, includes primitive functions such as support for security, low-level functions, and process arbitration. Finally, advanced functions are being loaded, such as file system, directory structure, and third-party add-ons. And then lastly, the graphical user interface is loaded. So again, you can see there's a lot of complexity, and there's a need for extensibility because of the different add-ons that may exist, but also compatibility. So a very interesting piece of software, the operating system. And in the next videos, we will review in more detail how it protects and defends itself.